Yeah, so with this talk, I was considering making slides, and then I decided doing the ASCII art diagrams is going to be a bit of a pain in the ass. And Brian thankfully loaned me his the setup that he does lectures with, so I can just kind of wing this, do it live, and I could go drinking last night instead of making slides. So this presentation does exactly what will probably go exactly as you expect. So I'm going to be talking about the 5V, which is basically a fork of 5E that I made to do Valgrindy stuff. So 5E, that's our MIPS emulator, or sorry, our ARM emulator, ARM32. It was written by IU several years ago, and it's basically it takes a binary, an ARM binary, and runs it in our system as though it was just a. It's not a full system emulator. It does the syscalls, it does the file I/O, but runs a MIPS. Why do I keep saying MIPS? An ARM binary in our system as though it was a binary on the native, running on the native system. Having this in the way allows us to do a whole bunch of stuff. So I'm going to take a step back and talk about why we care about doing Valgrindy stuff. What is Valgrindy stuff? Most people here have probably written some C programs. And in C programs, you've probably seen segmentation violations, you've seen panics, you've seen all sorts of bugs where you have an array, for example, and you write to array index, you've got 0, 1, and it's a 4-element array. So you want to write to the last element, and you write to element 4. Oh shit, that's not actually in the array. C is kind of C is famous for allowing these kinds of out-of-bounds writes, out-of-bounds reads, accessing of uninitialized memory. So for example, if you have a function stack and you're calling f of 1, which does, I don't know, int x, and you do return x, or f of y, well, you push y, and then you make room on your stack and return x, which, what's the value of x? I don't know. It was on the stack somewhere. So C does very little to protect you from this. So how do you deal with this? Well, the traditional Plan 9 solution for this, it works pretty well, but it's not really scalable. Plan 9 solution, get good at thinking about this. Don't make those bugs. Now, the rest of the world kind of went, well, our programmers are, they keep making these mistakes. We need to figure out some way to help them solve them, help them debug them quickly. So there are tools out there called Valgrind, Address Sanitizer, Electric Fence, I think, was one of the early ones, Mudflap. You can come up with a whole taxonomy of them. And they all do the same or similar things in a different way. So Valgrind, for example, is wow. This I'm not good at writing. Valgrind is basically a full system emulator, or not full system. Sorry, binary emulator similar to 5E. Whoops. Let me erase. Good enough. It's a binary emulator. It emulates the x86 architecture well enough to run whatever programs you need. And as it emulates things step by step, what it does is it will basically check that you're accessing things within bounds. It hooks your malloc implementation and goes, hey, are you within the array? Are you reading uninitialized memory? So that's how Valgrind works. Address sanitizer is a similar idea. But what it does is it takes the, it's actually, well, address sanitizer is slightly more interesting because what it does is it modifies the compiler to instrument the binary, where if you access something that's out of bounds, the compiler will access a shadow map. It will check whether the value's been initialized and so on. So I'm kind of grabbing ideas from both of these, and what 5e is doing is, it basically does this kind of, it does the emulation, which is nice, and then, but it uses the same shadow map idea that ASEN has. So I mentioned this term shadow map. I should probably explain what it is. So whenever you have a binary, it has several memory segments. And so actually, I'll do one more. It's got its text segment, data segment, BSS, and stack. So what we want to do is kind of keep track of the state of these segments. And a shadow map is basically, well, what if we took every byte in each of these maps, or each of these segments, and assigned a few bits of state to it? So, for example, so Valgrind does this with a single shadow map, where you cover the entire program's address space, steal a chunk of it, and put it out in the out of the way, so that if a stray pointer happens to happen, it probably won't corrupt your shadow map. In 5v, what I do is I just don't put this into the address space of the program, because this is an emulator. It doesn't have to expose everything. So whenever I access a byte, I basically take the address, divide it by 4. So I'm assigning 2 bits of state to every address. You have alloc. So every address can be either allocated or not allocated. And init, so initialized. Has it been written to before it's been read? Or has it been written to? So when you have a program that does something like x equals, or p equals malloc 3, I'll do char pointer p equals malloc 3. So I'm mallocing 3 bytes. Then I do p0 equals 1, p 1 plus plus return p4, for example. What will happen is that I will take I'll hook malloc, so I'll use the libmock to find the address of malloc. When the PC in the emulator hits that PC, I will record the return address, and when malloc returns, I'll basically say, hey, we allocated this much memory. Let me go into the shadow map and mark these bytes here as initialized, or as allocated. So you get the state of the shadow map for ... 1 0 1 0 1 0 0 0 0 ... So basically, these 6 bytes represent the state change from malloc 3. Then when I hit the P1, P0 equals 1, I'm initializing the first byte. So this becomes 1, 1. The byte is both allocated and initialized. When I try to access P1++, well, I'm reading from a byte that is in the alloc but not initialized state. So the emulator goes, oh, you're trying to do something funky. Let me pause the program. And 5e has something very nice where it also serves a fake /proc. So you can just attach with acid, debug, see what line you're at, what the state of variables are, what's going wrong. But let's assume that I find the bug, I fix it, and say P0++. OK, so now I've fixed the program. And here it'll get to the state where, OK, I'm trying to return from a value from P4. P4 is somewhere out here, 0, 0. Oh, shit. Well, I guess we've gone off the end of the array. You're accessing unallocated and uninitialized memory. OK, this program is garbage here, too. So we can detect these kind of memory issues using the shadow map. Maintaining the shadow map is a bunch of overhead, but the programs still run. I haven't actually benchmarked, but they run well enough that you can actually test some reasonable size programs. The compilers actually will compile running under 5e. So, although, yeah, so what are the so obviously maintaining the shadow map, you need a bunch of hooks. So you need to hook malloc, you need to hook free, but also you need to be able to handle the segment allocation or segment functions like segbreak, which is used by a bunch of programs for allocating memory that they know is zeroed, but it's also used inside the malloc. So when malloc is called, you have to disable the seg tracking so that you can so you can mark the memory as uninitialized rather than initialized. You also need to hook the other syscalls that might not be quite as obvious, like read, write, and so on, because you need to. And the reason you want that is because you want to be able to detect when the kernel would be accessing memory that's initialized or uninitialized or whatever else. The last thing that's probably OK. So that's roughly how this works, and that's roughly the current state of what I've implemented. There are a bunch of things that are missing from this still. Big ones. There's at the moment, there's no good way for me to find the stack size for when you take a function call. So when you have your program stack and you call a function, and then you call another function, and then you write to some stuff, and your shadow map gets updated. So, these values are all marked as valid because you've initialized them properly, and then you return. Well, I have no idea how much of the valid stuff needs to be cleared as invalid now. Yes?
Maybe you can track stack pointer updates.
Yeah, the big problem is that at least on ARM, I think we have a convention, but yeah, it could possibly track stack pointer updates. But then when you call the next function, well, all the stack is valid. So this is kind of the big thing that's missing. The other thing is that when you call a function, yeah, I guess stack pointer updates would work. But it's not implemented. So this is roughly the state of things. This is the whip. This is the big idea. The other thing is that there are a whole bunch of things I would love to have. Oh yeah, the other thing is that it needs to know about the ape allocator if you're ever going to run allocation function. If you're ever going to debug ported programs, it doesn't. And it doesn't actually know about global objects or add red zones around variables. So if you have an array followed by another array, and you access this array from this pointer, but then you access out of bounds in this array, this arrays will be marked as valid because, hey, you initialized it correctly. It doesn't know about different regions. So there are a couple of different options that I'm considering. One is that maybe I waste a bunch more memory in the shadow map and basically tag each object with the pointer. The other is that I teach the compiler to just kind of leave gaps around everything. So most accesses that are out of bounds will go only a little bit outside, or most of them will only go a little bit outside of the object. So you don't get random stray pointers all over the place. Or if you do, it's because that pointer was uninitialized, so you'd already trapped the access. So this is one thing I want to do. The other thing is that if you've ever used Valgrind or ASAN, there's another suite of tools around it, like Thread Sanitizer, where it'll actually instrument and watch for atomic accesses. And from my understanding, what it'll do is it'll build a vector clock for every memory address that's been accessed using an atomic instruction or is protected by a mutex. And then if you can't establish a total ordering on these memory accesses, you've got a race condition. So if you can't use a Lamport clock to establish a happens before on every access. This would be something else to play with. And then the other thing that I would really like to do is actually throw this all away and put it into the linker. So having this running in an emulator, I'm not sure how fast. As I said, I haven't benchmarked what this 5V looks like, but Valgrind gives you roughly a 20 times to 40 times slowdown. I assume that this is probably going to be closer to 100 times, just because there's been zero work going into optimizing it. It allows multi-proc programs to be tested, so there's a lot of mutex contention around just boring memory accesses. Or there's a lock around every memory. There's an RW lock around every memory I/O. So I think that putting this into the linker, teaching the linker how to actually generate the instrumentation around the memory reads, memory writes, and using a shadow map and putting a shadow map in as a separate segment would probably be a more interesting or more useful way of doing it. The other thing is the linker already knows exactly how much stack space is being allocated for each function, so it can generate a clear shadow stack operation at every function call or at every function return. Anyway, that's more or less the summary of what I've been working on. This whip feels like it's more whip than others, and we'll see. It has been useful for debugging a couple of small programs for me, but there's more work to be done. Any questions?
Yeah, very quickly. So just to make it clear, so you have full emulator, like full interpreter, you can run it on x86, so you need ARM host.
No, full interpreter. The reason it's ARM is just because we had the ARM interpreter lying around, and it had hooks in exactly the right places for every memory access where you got the bits for what the operation was, what the value was, and what the address was. So there was one place where I needed to change the code.
But you're still using the host kernel, right? For the kernel.
Uses the host kernel. You just point a binary at it, and it'll run it. It feels very much like using Valgrind.
This is for the linker idea. Would the idea, are you going to blow up the binary sizes, or are you going to do something that...
Yeah, the binaries will end up being probably I'm going to guess 2 or 3 times the size, because you need to, after every memory read, you could do some stuff where you verify, you basically float the access check up and avoid repeated ones, but it'll grow the binary size quite a bit. You'll probably, if the most naive option is you basically insert a function call or a jump to a small check for every memory access. ASAN, so address sanitizer, I assume they've got optimizations, but supposedly in production they're about 2x slower than running a regular binary, and I think that there's probably going to be, like, we're not going to hit that because I don't think we're going to be, the first implementation is going to be naive, and we don't have the loop invariant code motion that you would have in a Clang, or we don't have the some of the other compiler optimizations that would be able to kind of go, oh, this check has already been done up here. We can just eliminate this one. We could work towards that. But yeah, 2x binary size plus.